Hey guys, in a recent video, we talked about different ways that you can speed up the rate of a reaction. We talked about how heat can speed up a reaction. Reactions tend to go faster at a higher temperature. That's a really hard and fast, good rule of thumb. One that we hadn't talked about, increasing the surface area. I'll explain that in just a moment. That can also increase the rate of a reaction. And the third way, catalysts. And in fact, all three of these ways of speeding up a reaction are good evidence for something called collision theory. And we're going to talk about collision theory and effective collisions as well. So you're familiar with kinetic molecular theory. Kinetic molecular theory is this idea that if you have a sample of matter, the atoms are moving around, jostling, rotating, vibrating, bouncing into one another. In the gaseous state, that's what's responsible for the phenomenon of pressure. But even liquids and solids are jostling around a little bit. But of course, it's much more vigorous with gases. So that was kinetic molecular theory. And all of the gas laws, Boyle's law, Charles' law, Avogadro's law, they all sort of emerge naturally from the assumptions of kinetic molecular theory. Collision theory is related to that. And the basic idea is that you need collisions for chemical reactions to occur. So before we talk about how these things are actually evidence for collision theory, let me explain what collision theory is. So if you would please turn to this page in your packet. It's towards the end. It says collision theory at the top. And we're going to look at a particular reaction which involves one reactant, and I'm not sure how to call this compound, bromine, not sure. Bromine and nitrogen oxide. Anyway, it doesn't matter what it's called, but two of these molecules apparently collide with one another for the reaction to occur. So we start off with 2BrNO, and those are that's the one reactant, I suppose. And then there's two products that form, and those are nitrogen monoxide and diatomic bromine, which is a liquid at room temperature. Okay, so we've got these gases, and they collide, and we get the products. Okay, so let's have a look at maybe how this reaction occurs. Okay, so this is sort of assuming a one-step process, and it may or may not be, but it seems to be reasonable to think maybe if two of these molecules smash into one another, that we could get the products. So, and it turns out the orientation in space of these molecules really might make a difference. Here we can see these molecules kind of moving together, kind of on their sides. In the second picture here, you can see that they're coming straight on, head on towards one another with the bromine atoms that are hitting. But each time it's those bromine atoms that are hitting. And so maybe in order to have an effective collision, those molecules need to hit in a particular way, because we can imagine, if we're going to form some diatomic bromine, it's probably important for those bromine atoms to get close to one another and interact. Okay, so there could be effective collisions. These two right here would be effective collisions that lead to the products forming, but there could be an ineffective one as well, and there's probably lots of ways for it to be ineffective, but there's an example, because the bromine atoms didn't even come into contact, and so now these two molecules of Br and O just bounce off of each other. Okay, so effective, which leads to the chemical reaction happening, and ineffective, which is just like a ping pong ball bouncing off of another ping pong ball. Okay, so it seems to be important that these molecules have a correct orientation, and it's also important that they hit with enough energy for some of those old chemical bonds to break apart and for new bonds to form. Okay, so let's go ahead and define what an effective collision is. And keep in mind that not all collisions are effective, but an effective collision is a collision, of course, that leads to the chemical reaction happening. So effective collisions have enough energy. We can imagine if maybe the molecules collide very, very slowly and lightly. Maybe there's not enough energy to break them apart. Okay, if you imagine if you got two magnets that are stuck together and you just drop them on the floor, they might stay together actually. But if you throw them against the floor, the two magnets might break apart. You got to have enough energy to break apart chemical bonds in the same way. So you got to have enough energy in the collision, and it also seems to be reasonable to think that the orientation in space might make a difference. Probably does. So have enough energy in the collision, and the molecules are oriented in space. Excuse me, oriented in space appropriately. And those are going to lead to the chemical reaction happening. Okay. Okay. So how would all of these three things, which we know speed up chemical reactions, how would these support collision theory? Well, heat, of course, makes molecules move faster. At a higher temperature, there's more kinetic energy. And so that means there's going to be more particles that are hitting one another with enough force to cause the chemical reaction to occur. Okay, and I have a graph of that scenario down here at the bottom, and I want to go ahead and talk about that. It's this one right here. It's the effect of increased temperature. So temperature 2 apparently is the higher temperature here in this graph. And here we have the number of collisions on the y-axis and just the energy of the collisions on the x-axis. Okay, so you've got some collisions which are very, very low in energy, so they're just sort of, you know, hardly colliding at all, like two snails colliding. And then on the other end, you've got some really, really energetic collisions. Most of them at the first temperature are somewhere in here maybe. So there's, you know, they're fairly energetic, but notice it's below a threshold energy. This energy right here is called the activation energy. And the activation energy shows up on these other graphs as well, and so it's an important concept to keep in mind, but this is sort of like that energy that we need to put in order to break some chemical bonds, okay? Now, if we increase the temperature up to this higher temperature, temperature 2, right, that's this curve here, here we can see that a lot more of them have higher energy, so I'm not sure where the average value would be on that curve. It's not exactly in the middle, but probably close to the peak somewhere in here, but it's more energetic collisions. Okay, so as a result, at the lower temperature, maybe you had, you know, X number of collisions, but at this higher temperature, a greater proportion of those collisions are high energy collisions, enough to get over the activation energy. So you're still having perhaps maybe even probably not the same number of collisions. You're going to get more collisions, but what's really important is a greater proportion. Now have that activation energy, EA. Okay, and so the chemical reaction goes. Okay, so let me talk about what this activation energy actually is. On this first graph up here, this is a really clear picture of the activation energy, and you can see it right here. It's the height of this hump. There's this hump that we have to get over for this chemical reaction to occur. By the way, this chemical reaction, can you tell if it is exothermic or endothermic? Just by looking at it, can you tell if it's exo or endothermic? If you said exothermic, you're right, because all that matters is where you start here and where you finish down here. And so you can see that this gap right here, we've sort of dropped in energy from the start to the finish. Okay, so this is less than 0, the system is releasing energy. It's releasing some of that energy that was stored in the chemical bonds. But also important is there's this hump we have to get over, okay? And imagine you had some type of ball you're rolling over a hill, right? If you don't roll it hard enough, it might just roll right back, right? So if you had the ball here and you roll it up, you've got to get it to the top of the hill before it even has a chance to go over the other side. And it's exactly the same with chemical reactions. You've got to put in enough energy to get them to go all the way to the product side. Okay, and here at the top, there's something called the transition state. Okay, so the transition state occurs at the moment these molecules have come together and you've disrupted and broken all of the old bonds. And it's the instant before any new bonds form. So we've broken all the old bonds and no new bonds have formed yet. And so we've drawn these molecules in here with these dotted lines, and that indicates sort of an unstable, high energy system, okay? And what is going to be favored then is the bond between the bromine atoms, and these bonds right here are going to be broken, okay? And so that's what we end up with over here. So this is the heart of a chemical reaction. It's just atoms being combined in a new way, but in a more favorable way for a spontaneous reaction. And a lot of time that's exothermic with stronger chemical bonds. Okay, so we have this transition state. You should also know that there's a synonym for transition state. Sometimes people call it an activated complex. A complex is a number of atoms arranged in a particular way, and activated means that it's high energy. So you have a high energy complex, an activated complex, also called the transition state. I've got a nice visual of a transition state. You guys may have seen this in my classroom. There's this little ball thing. It's called a switch pitch, and I'm not sure if I can do this on camera, but if you throw it up in the air and then you catch it, right, it kind of turns inside out on itself. Okay, right, and so you can kind of go back and forth one way or the other, and this represents a chemical system. Actually, you know, you can think about the moment where if you put in enough energy, you know, it might go either way. It's sort of like this system is sitting at the top of the hill, and it could go blue or it could go pink. All right, and if you put in enough energy, it'll go the whole way. Okay, so that's a nice visual for the transition state and this whole idea of getting in enough energy, right? So in theory, maybe if you just kind of blow on this a little bit, it might go, but probably not. You got to put in enough energy for it to go all the way. Okay, so the collisions in a chemical reaction have to be effective collisions. You got to put in enough energy to get it over the transition state towards the products a little bit closer. Okay, so let's summarize. Heat speeds up a reaction for two reasons. You get more collisions total because particles are moving faster. All right, so you're going to get more collisions total. That's like more pressure, you know, in terms of gas laws, right? More collisions, more pressure. But also, the collisions that are happening are also high energy. So that necessarily means more that have the required activation energy. So the reaction goes faster since more are able to get over the hump. Okay. Now, what about increased surface area? A good visual for this idea is imagining you have a Alka-Seltzer tablet. If you're not familiar with Alka-Seltzer, it's a little medicine tablet you can put in water and you drop it in and it fizzes and there's this chemical reaction that's happening. And so you can actually try this at home. If you have an Alka-Seltzer, you might try this. Open up a pack, get 2 cups of water, drop one in just as a solid tablet, and grind up the other one into a little powder. And the one that's in the powder form, it's going to bubble much more quickly than the one that's the solid tablet. Okay, so you're not really changing the amount per se, and this is not even really concentration, but you're getting more surface area. And so when you increase the surface area, why in the world would that cause the reaction to increase? Well, collision theory helps us understand why. Imagine that scenario with Alka-Seltzer. Remember, water molecules are involved somehow, and they are reacting with the Alka-Seltzer. Okay, and if we allow the water molecules to have a lot more surface area, there's instantly more collisions. Okay, when the water molecules can hit it from all sides instead of just on the outside, really, in the powder form, you've got a lot more that's on the outside. That's what surface area is. And so you immediately get a lot more collisions. And that's not because the particles are moving faster. It's just now there's a lot more opportunity for that to happen. And probably also a lot more opportunity for the right orientation and space of the molecules as well. Just by sheer numbers, you're going to get more that have the right energy and the right orientation. So this just leads to more collisions as well. So we get more collisions instantly because there's more surface area. Okay. Similar idea if you've got, you imagine a skydiver. If you're skydiving and you're pointed horizontally as you descend through the air, you got a lot more surface area. There's a lot more collisions of air particles against your body, and it slows you down a lot more. But that's the whole idea of collisions. So there's a lot more collisions when there's more surface area. Okay, so more collisions, and therefore more effective collisions. Okay. The proportion of effective collisions is probably the same. It's the same temperature, but since you've got more collisions per second, you're going to have more effective collisions per second as well. Catalysts. Mentioned this a while ago. There's important chemicals in your body called enzymes, and without catalysts, without enzymes in our bodies, the temperature would have to be a lot higher in our bodies for some of these really important reactions to occur, and that could be fatal for us. Our body temperature needs to be around 98.6 degrees Fahrenheit, give or take a few tenths of a degree either direction, and otherwise it can really cause problems for our body. And so it's really good that we have these enzymes in our body, because without them, some of these chemical reactions would just not be very efficient. Okay, so let's look at the effect of a catalyst and talk about how this might happen. These three right here, these three graphs illustrate the effect of the catalyst. Okay, so what the catalyst is going to do is it lowers the activation energy. So I call this the high jump effect. Or the high jump bar effect. There's probably very few people at Landmark who could high jump 6 feet right now. If we all went down to the track there at Landmark, at Thorne Stadium, and we lined up everybody from pre-K up through 12th grade and the faculty and staff, there might be 1 or 2 people. I don't even know if there's anybody at Landmark that can high jump 6 feet right now. Maybe I'm wrong. That'd be a pretty tough amount of height to clear, right? But if we start lowering the bar little by little, we're going to eventually get more and more people who are able to clear that height. Okay, so as we lower the bar, the people with their abilities that they already have, they'll be able to high jump a lower height, okay? And so that's what a catalyst is going to do. So it lowers the bar. You know, if you want to immediately become a better teacher, it's really simple. You know, you just make the tests really, really easy, and then that's lowering the bar, and more people are able to get A pluses, and so that makes you look really good as a teacher. Of course, that's not really indicative of ability necessarily, right? If I lower the bar, or if you lower the bar on high jump, you know, having a lot of people high jump 3 feet is not necessarily indicative of like an amazing ability, right? But if you want a chemical reaction to go faster, this is a great way to do it, okay? So we lower the activation energy. So let's have a look at these first two graphs. Notice, first of all, that these curves are identical. Those curves have to do with the temperature, the number of collisions with a particular amount of energy, and then the actual energy per se. So these are similar Maxwell-Boltzmann curves in terms of how the collisions are happening. But if we can lower that energy, let's say that this is 100%. I don't know what the units are on here. There's no units. But if we lower it down to, kind of hard to say, if we lower it down to like 80%, okay, that'd be a lot easier to accomplish. And so you're going from a certain number of effective collisions to a much larger number of effective collisions just by lowering the activation energy. We see the same information just in a different way here on this graph. In fact, it's actually a little bit different of a bit of information. We're seeing the energy and the reaction progress on the x-axis. So this is an endothermic reaction. You can see that we're going up a little bit in energy from start to finish, so it's endothermic. But the first curve is the uncatalyzed pathway. So you can see that there's a really high activation energy. So this one in blue here is the activation energy. Now on the catalyzed pathway, right, on the catalyzed one, there is a much lower activation energy. Okay, so this one right here, significantly lower. I didn't quite draw those well. Let me do that in red and green instead. So here's the activation energy on the uncatalyzed pathway and the activation energy on the catalyzed one. Okay, so of course you can see that that's a lower hump to get over. So that's the high jump bar effect. Okay, the way that catalysts work, I mentioned this last week, or excuse me, before spring break, is well, of course, they lower the energy requirement. They create a new pathway, right? There's a new pathway which has a lower activation energy. It doesn't magically change the activation energy. There's a different path. So this is like sort of taking a different route through the mountain range to go from, the bottom of the mountain to the cabins that's halfway up somewhere. So you can take a different route. So we create a new pathway which has a lower activation energy. Okay, and let me put that in black just to be consistent here. And an important type of catalyst you should know about, they're called heterogeneous catalysts. Heterogeneous catalysts are often some piece of solid material, and it's not a reactant. It doesn't react away. It just kind of stays there. But its purpose is to create a surface for the reactants to kind of aggregate and accumulate. It's a process called adsorption. It's kind of a hard word to say. Often a solid where or on which reactants adsorb. Of course, you're familiar with the word absorb, A-B-S-O-R-B, but this is A-D-S-O-R-B, and that's molecule by molecule kind of getting stuck into another substance. So reactants are adsorbed, and so you get a little localized increase in concentration. Sort of a small localized increase in concentration. Okay, and so let me give you an example of a heterogeneous catalyst. You might be familiar with catalytic converters that are in our gasoline-powered automobiles. There's all sorts of exhaust fumes that come out of the exhaust pipe of internal combustion engines. And one of those substances is carbon monoxide. Okay, so inside of petroleum or gasoline, there is a bunch of different types of hydrocarbons, and we'll just say CXHY for your general hydrocarbon. It might be octane or propane or heptane. But when those burn, the major products, when you have really good combustion, a clean burn is carbon dioxide and water vapor. And of course, carbon dioxide causes its own problems. It's a greenhouse gas. But sometimes you have incomplete combustion. And so instead of forming carbon dioxide, you get some carbon monoxide. Okay, and that's sort of a hazardous substance along with some water. Now this carbon monoxide, as it passes over a catalytic converter, it gives it a little bit more time for oxygen to react with it. That's one way to think about it. And so it lowers the activation energy. So at a given temperature, maybe there wasn't really good clean combustion or something, but carbon monoxide gets a chance to react a little bit more with that piece of platinum. So sometimes people write the catalyst on top of the reaction arrow, and that signifies it's not a reactant, but it's present and it's helping the reaction to occur. So, and that leads to more carbon dioxide forming, which is a bit better for the environment. And there's other substances that have nitrogen and oxygen that can be hazardous as well, and the catalytic converters help deal with those. And so it provides a surface where you can kind of accumulate a bit more of the reactants. They kind of slow down a little bit more, and that's actually advantageous because their concentration increases a little bit, and it gives a location for the collisions to occur. Okay, so for these three factors that we know increase the rates of reaction, we have a rationale for each one as to how it helps collisions lead to the products forming. Okay, so we've got to break the chemical bonds, right? We've got to break the bonds, which requires energy. And that's an endothermic step, going up in energy. And then the exothermic step is going down the other side where we form the bonds.